video of this lesson. So we'll see if that actually works. The only problem is I can't see it. Can't see what I'm looking at. But anyway, I'll figure it out. If you see me going like,
yeah,
you can feel free to tilt that around if you want to. Anyway, yeah, so we more or less finished chapter 2 on Tuesday, where we were talking about Diophantine equations and how to solve them. I'm going to jump into something new today. Again, that's why I don't have a recap up here. Chapter 3 in our book is all about primes. And you can't get very far in number theory without talking about this. These are like the building blocks of the whole integer number system. So, this is kind of important. It's kind of like atoms of the universe. They are the building blocks of everything. So we have to have a pretty good handle on this. I'll start off with just the definition. Again, I know that a lot of you know these basic things already, but just so we're all in agreement about what the terms mean, an integer, which I'll call p, greater than 1, is a prime number So notice that 1 is not considered prime. So it has to be greater than 1. If it's only positive divisors are 1 and p itself. So a prime is just a number whose only positive divisors are 1 and p, which would, of course, be divisors of p, but that there are no others. All other integers greater than 1 are called composite. They're called composite numbers. So every positive integer greater than 1 is either a prime or a composite number. A composite number would be just one that has some other divisor other than 1 and itself. Okay, so that's just the definition. And then almost as well known as the definition itself is this theorem that I'm about to write down, which characterizes one of the important properties about primes. So this is a special property of primes. Namely, if p is a prime, so this is a theorem about prime numbers. If p is a prime, and let's say that p divides a times b, then in that scenario, p divides a or p divides b, or possibly both. Okay, but it divides at least one of the two numbers. So this is a really helpful way to think about prime numbers, and it's not too hard to write down the proof of this, so I would like to include it into the notes here, guys. After all, it's a theoretical class. There's going to be a lot of proofs. Whenever you're trying to prove an or statement, it can be, it's like, well, I don't know. Which one is it going to be? We don't know, so we don't know what to aim for. The way to always prove something like this is to assume that one of them does not hold, and then that therefore forces the other one to automatically hold. So to set this up, I'm going to assume that p divides ab and that the first possible conclusion fails. So p does not divide a. So p divides ab and does not divide a. And then we will show that therefore p divides b. In other words, if p did divide a, the other way to do it is to just say, well, if p divides a, then we're already done. And so therefore we may assume that p does not divide a and go from there. And in this case, we would know that the greatest common divisor of a and p, what would it be? It would be 1, exactly. Because the only positive divisors of p are 1 and p, and p is not a divisor of a. So if you're looking for a common divisor of them both, right, the only thing left would be 1 as the only possibility. And what do you suppose I'm going to do now? I have p divides ab, and I know the greatest common divisor of a and p is 1. So where do we go from there? Apply Euclid's lemma from the videos that you guys watched last week. So by Euclid's lemma, told you that thing was going to be helpful. Right? By Euclid's lemma, P divides P. Super short proof, nothing too hard about that. Okay, so that's the first property about primes that we want to know. Now, there's a couple of corollaries. The book just numbered these with respect to the results. So corollary 1 and corollary 2. The first one is that if P divides a whole product of numbers, let's say that it divides A1 times A2 times A3 all the way up to A sub n, then P divides A sub I for some I. Okay. So in other words, if it's not just a product of two things, but it's actually a product of more than two things, we kind of get the same conclusion. You could prove this, for example, by induction on n. So prove induction on n would be fine. You would want to use the n equals 2 case as a base case. So to get the proof going. So with n equals 2 as a base, and of course the n equals 2 case we've already done. So this would actually be the base case for the induction would be here, because over here I have two things, A and B. And once you've got that, you'd be able to take a product of n things and view it as sort of two things, like group these together, and so that you'd have just two things there. Yeah. Okay, so that would be easy enough. I'll leave the rest of the details of that for you to fill in. The second corollary is just going to immediately come from, sorry, I really should say, so corollary 1, back to the first corollary, assume that P is prime. I mean, I think we know that, but we really should be careful. Assume P is prime. I meant to write that. Because if you wrote that on your homework and just started using a P without saying that it was a prime, I'd be like, well, I'm not sure what you mean by that. So we should always clarify that. Don't just assume that I'm going to know that that stands for a prime. And I need to do the same thing here. So assume P is prime. So corollary 2 starts off exactly the same way. In this case, if P divides Q1 times Q2 and times ... up to Qn, where each Q sub I is prime. Okay, so that's a little twist there. Then, so if this right-hand side consists exclusively of prime numbers, then your P is actually equal to one of these primes that we're talking about. It equals Q sub I for some I. Right, so this is a little bit stronger conclusion that we can obtain basically from here. Let me write down the proof of corollary 2, which is not anything too lengthy. I'll just get it in here for the record. So for the proof, you would start off by applying corollary 1, right? So assume P is prime and P divides the product of Q1 and Q2 and ... up to Qn, where the Q sub i's are prime. Okay, so by corollary 1, the P divides the Q sub I for some I. But now we have one prime number dividing another prime number. They're both primes, right? So we can look at this Q sub I, we can say, well, we know it's prime. Oh, and here's a divisor of it. So any divisor of a prime has to either be 1 or itself, but P is not equal to 1 because P is prime. So since P does not equal 1 and Q sub I is prime, then we immediately know by the definition of a prime that P must be equal to Q sub I in that case. Get a little bit stronger conclusion, which is what we were hoping to prove there. Okay. So far, so good. Just interrupt me with questions if you have any as we go along. I'm about ready to state one of the most important theorems in this entire class. So we've got the basics about prime numbers down here, obviously, but why are they really, really important? I kind of hinted at this already, which is that the prime numbers are the building blocks of the entire integer system. And what we mean by that is that every integer can be built out of a collection of primes. And that is stated very formally in this next result. And we certainly want to know this one. This is a graduation worthy theorem. You guys know what I mean by that? I used to be, I don't know, I got fired from the job, but I used to be the commencement marshal or whatever. And I was like the guy who walked the people in to the ceremony at the end. And then they had me sitting right there with the students because I was kind of the usher. So I was basically just an usher. But I got to sit like right there at the spot before the students read. The last person they're going to have to look at before they go to the stage for their diploma was me. They had to walk past me. And I always liked to sort of use that as a little point of leverage on my part to see. So you took my class, so just I want to make sure this is no mistake here. I've got a couple questions for you. And so if I had a graduation worthy question, I could ask it and stop all the music. Let's just wait. It's one last. Just have to make sure this is really not a mistake. So anyway, I got fired from the job, maybe because of that. Too many people complained. But this one would be the kind of thing that, you know, would be worthy of that. It's a really important result. This is the fundamental theorem. The fundamental theorem of arithmetic. The fundamental theorem of arithmetic. So you've probably heard of a fundamental theorem of calculus and a fundamental theorem of algebra. Like, it seems like every class has one of these. So this is a relatively easy one, the fundamental theorem of arithmetic. And here's what it says, guys. Very, very simple to state this result. Every positive integer, I'll call it n, which is greater than 1, can be expressed uniquely. That's an important word, obviously. Uniquely, every positive integer greater than 1 can be expressed uniquely as a product of primes. Now, this is the point, right? This is the point. Every positive integer greater than 1 can be expressed uniquely as a product of primes. A very simple theorem to state. But unlike many results in number theory, this one's actually also pretty easy to prove. So I'm going to do it. Definitely something I will want you to be able to prove. So you'll see it's very logical. There's no real weirdness to it. Kind of goes how you would expect. There's really two things being stated here. There's a uniqueness statement and an existence statement. The fact that you can do this, you can express n as a product of primes. And then secondly, that it's unique. I'm going to start with just the existence part first, and then we'll do the uniqueness second. The existence part is actually the easier part, so let's just take that on to begin with. And we're going to actually do this existence by using what's called strong induction. So of course you guys know, and I kind of talked in the video about induction again, there's sort of the regular induction where you assume that it's true for n and then you prove that it's true for n plus 1. Well, that's not going to be very helpful here because the primes that are made up in the factorization of n plus 1 are not going to be anything like the primes that are in the factorization of n. So going from n to n plus 1 is not going to be a natural move to take. But strong induction actually allows you to assume that your statement is true for all preceding values of n, not just the one previous one. So that's why I say this is strong induction. So I still have to do a base case. The first integer greater than 1 would be 2. So that's my base case. So for, I'll just call this a base, I guess. For n equals 2, well, that can be viewed as a product of primes. It's only one prime, but that does count. So for n equals 2, n is already prime. And I mean, there's really not much to say here. You're already kind of good to go. You have a prime, and a prime itself is a product of primes. Okay, so now consider arbitrary n that could now be more than 2. So we just pick some larger number. Of course, if n is prime, again, that's possible. If n is prime, then of course we are done again by the same reason that a single number that's a prime can be thought of as a product of one prime. Okay. Just make sure that I'm getting, I move this over here so it's a little closer. Somebody interested to see if this is going to be a better recording. Okay, so if n is prime, then we're already done. Otherwise, it's composite. And if it's a composite number, then there's some other divisor of n besides 1 and n, and we can use that to factor n. So otherwise, what I'm going to do is we can factor n as n equals, let's just say a times b. So it would just be a product of two numbers here, like a times b, where now the factor that I'm looking at is not 1 and it's not n, right? For a composite number, there's some other factor. So the a and the b are both going to be larger than 1 and smaller than n. So strictly, right? Strictly greater than 1 and strictly less than n, as I've written there. Okay, so because a and b are strictly less than n, I'll be able to use the induction assumption on them. So I know, for example, that both a and b are already expressible as a product of primes, and then you're just going to shove those factorizations together to make a longer factorization for n. So I think you guys get the idea. Let's just write that down, and that'll do it for the existence part. This is not too terribly hard. So by strong induction, we may write, in fact, I'll do them both kind of here together. We can write both a and b as products of primes. So a might be p1 times p2 times ... times pr, and b might be q1 times q2 times ... all the way up to qs, right? And this is just where the p sub i's and the q sub j's are primes. These are all just primes that are making up this product. And so thus, let me know if I'm going too fast, guys. Let's get a little excited here. But the a and b are written as products of primes. So then n, which we've already explained was equal to a times b, is literally just the concatenation of these expressions for a and b. So p1 times p2 times ... And then once we get to pr, we just start with the q's, q1, q2, up to qs. And sure enough, n is a product of primes. So this is a product of primes. Good enough, right? So that shows the existence of a expression of n as a product of primes. So far, so good. What actually gets used more often is the uniqueness part. It's actually more often the unique. In fact, so if you wanted to prove, for example, that the square root of 2 is irrational, right? You could say, well, suppose, I'm just gonna scribble here for a second, don't need to take notes on this. You can suppose by way of contradiction that the square root of 2 is expressed as a fraction like this, and then you can just kind of clean it up by cross multiplying and then squaring both sides, right? And then what you can say is, well, how many factors of 2 do you have on the left side? And how many factors of 2 do you have on the right side? I don't know exactly, but I do know that there's an odd number of them on the left side, and there's an even number of them on the right side, because when you square the factorization, you just double the count of each factor. So you say, oh, well, you have an odd number of factors of 2 here, but you have an even number of factors of 2 here. Because of the uniqueness of the prime factorization, there's no way that those could be the same number, because that would represent 2 different factorizations in that case. So that's a really nice way to, maybe you've even done an exercise like that before, use number theory to prove something kind of analysis oriented about irrational numbers. So we always, algebra always comes first. Use that to then help you do all the other, the geometry, the calculus, all of it's all grounded in algebra. Just remember that. You can challenge your other professors on that one. Okay. What about the uniqueness? It's funny because, of course, a lot of results in number theory use branches of math like complex analysis to work on them, which does not sound like something on the surface of it that you would expect. But so these subjects are more intertwined than you might think. Uniqueness, well, you guys know whenever you want to show something's unique, it's good to just assume there's 2 of them and then prove that they're equal, right? Prove that they're the same. So let's assume that we've written n in 2 ways. First of all, it's equal to P1 times P2 times ... times PR. I'm starting over now, so these are not the same P's I was using earlier. And also, n is also equal to Q1 times Q2 times ... times QS. And again, the PIs and the QJs, again, these are primes. Okay, so you could just kind of suppose that, and then without loss of generality, if I write WLOG, is everybody good with that? Okay, I'm going to go ahead and assume that that's okay. Without loss of generality, I'm going to order these primes in increasing order. So I'm going to assume that P1 is less than or equal to P2, which is less than or equal to the rest of them, all the way up to P sub R, ... like that. And I'm going to do exactly the same thing with the Q's. So Q1 is less than or equal to Q2, and so on, ... up to QS. There's nothing that says that the same prime, that the primes have to be distinct. It's possible that they could repeat, so I have less than or equal to there. Okay, so now here's what we need to do. We're going to take P1. P1 is obviously it obviously divides n. I mean, P1 is one of my factors. It obviously divides n, which means it divides this product here, right? So P1 divides the product of actually all of the Q's. P1 divides Q1, Q2, up to QS. And of course, P1 is a prime. So you know where I'm going with this, right? We just had a corollary a short while ago that if you have a prime that divides a product of other primes, then it must be equal to one of those other primes. So by corollary 2 from above, P1 is equal to Qi, but Qi is definitely greater than or equal to Q1, because remember that Q1 was the smallest of the primes in the Q list, right? And of course, this is for some I. Okay, so what we've said is that P1 is greater than or equal to Q1. So P1 is greater than or equal to Q1. Well, actually, we could start this whole thing over with Q1 dividing all of the P's using the same corollary to say that Q1 is greater than or equal to P1. So similarly, basically just turning this around, similarly, Q1 is greater than or equal to P1, or in other words, P1 is less than or equal to Q1. And so I'm going to put those together and conclude that P1 is equal to Q1. So we're kind of going to prove that these two factorizations, let me kind of get these into everybody's focus here, right? I'm going to prove that these are identical factorizations. So I started off, the smallest prime here agrees with the smallest prime here. And you can imagine what I'll do next is cancel the P1 and the Q1 and then just play the whole game again, right? And just kind of knock them off that way. So let's do that. I'll just write something about that here. So canceling is the trick we need right now. So canceling, we get P2 times P3 dot 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 up to PR equals Q2 times Q3 times dot 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 up to QS. And just continue as above to show that P2 equals Q2, right? And then P3 will equal Q3, doing the same thing again. And we just kind of go dot, 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 dot. But we can't run out of primes on one side before we run out of primes on the other side, or we'll have a 1 equal to some primes that are left over. Well, that doesn't make any sense. So the R and the S actually have to coincide as well. So we continue to do this since both sides reach 1 via cancellation. At the same time. You can't run out of primes on one side before you run out of primes on the other side. We also have that R is equal to S. So this is pretty good. This is pretty good. P1 equals Q1, P2 equals Q2, P3 equals Q3, and you end up stopping at the same moment. So the R and the S also agree. That pretty much tells you that you're looking at the same thing here. These are the same factorization choices.
Yeah, quick question. When you mention corollary to there, you write PI equals Q or P1 equals QI. Should that not be J or is this the I?
It doesn't matter what letter I use at this moment. If you want to use a J there, as long as you put the J here, it's okay as well. I suppose in the corollary I was using a J maybe. I can use I. Okay, yeah. So it actually is just a arbitrary index subscript there. Yeah, good point. Okay, great. So we have that. So just to give you an example.
Oh yeah, Dr. Annie did use QJ there in parentheses though. He said PI and J.
Oh, here?
Yeah, so maybe it should be.
It doesn't matter. All right. Now are you happy? Just kidding. Okay. Yeah, no, that's totally good. Totally good. Makes sense. Okay. I found a problem in a math competition. And it was not any not like some Putnam problem or anything, but it was like an interesting little problem. And I thought, oh, well, that's using the fundamental theorem of arithmetic. I should put it into my notes. So I'm just going to show it to you really quick. And it's really intimidating to me when I look at these and it's like, oh, this was supposed to be for some high school students to solve. But that's the way it goes. You're going to find it, I think, pretty easy to solve it with me here. Basically, I'd like to solve for x. And so this is x squared minus 1 equals 17p, where p is prime. And I guess I should say that x is supposed to be solved as an integer, right? So just a little tickle your brain problem, but it's really having to do with factorizations into primes. The right-hand side is already factored as a product of primes, 17 and p. And that's a unique factorization of that number, which means that the number on the left side has to have exactly the same factorization. Can we factor the left side? Of course, we can take x squared minus 1 and write it as a product of x minus 1 times x plus 1. And one of these numbers, somehow, there has to be a factor of 17, or it has to be 17. So, you could look at these two things, they're 2 apart. Okay, but if x plus 1 was equal to 17, okay, well then, problem with that is then x minus 1 would be equal to 15, and that's not going to be a prime. So this won't, there's no way that 17 times 15 can match 17 times p. So this is a contradiction to the fundamental theorem. You guys can abbreviate this if you want, because it's kind of long. Keep writing fundamental theorem of arithmetic. So FT of arithmetic is good enough for me. So that can't be the case. So then the other possibility is, so next, try x minus 1 equals to 17. That's the only other possibility. So in that case, that would imply that x is actually equal to 18. And so x plus 1 would be 19, and that would be the p value in this case, because you've got, if x minus 1 is 17, then x plus 1 would need to be the p, so that you have 17 in p. And remember, this is a unique factorization, so there can't, well, could there be some other answer to this problem somehow? No, there really can't, because 17 and p are the only 2 factors. So x is 18 and p is 19. That's a nice little use of the uniqueness part of this fundamental theorem. Yeah, Kim.
So notice how x minus 1 and x plus 1 is a difference of 2.
Yeah.
And x in between it, so 3 consecutive numbers.
Mhm.
One of them divides it.
So we have 3 consecutive numbers there. Yeah, x minus 1, x itself, and x plus 1. Turns out in this case, x itself is the multiple of 3. Sorry.
We can conclude it from that statement after the consecutive number and the fact that if x minus 1 is 17, then the number of ways the x which is in between it.
Yeah. Yeah, absolutely. Yeah, so you just go here to here to here directly. Yeah, yeah. But it works really nicely. It's just a simple little problem that has to have a unique solution. So, okay. Great. Great. Let's see. You guys know how to tell whether a given number is a prime or not, or how to test besides using your calculator? Or the computer, all you have to do now is put it in there and say, is this a prime? It'll have an answer for you. Back in the old days, not that I would know about this, they used to have to like test possible divisors of the number up until a certain point. So, so just as this is sort of the brute force way of doing it. How to tell if a number is prime. Questions, how can you tell if a particular number is prime? And what you could do is, oh, you want to tell me? Yeah, you're just looking for divisors of that number. And so you can try prime divisors, right? So you can try 2, you can try 3, you can try 5, and so on. Those are the first few primes. Up until, how far do you have to test up until? The square root. The square root of that number, right? Because if you have not found any prime divisors up to the square root of that number, then you won't find any beyond that, because if you had any beyond that, then there would have to be a partner factor that's less than that already. Okay, so this is probably something familiar. So the answer here, I'll just write this down. Test prime divisors, prime numbers up to and including the square root of n. Of course, that's only if the square root of n is actually an integer, which a lot of times it's not. And if none is a divisor, then n is prime. Then n would be prime. So that's just a little sort of brute force way of testing whether a number is prime. This whole primality testing is a big hot topic these days because it's prime numbers, large prime numbers. I'm talking about primes that have hundreds of digits are important for crypto systems. And you need to know for your crypto system to be robust that it was constructed using prime numbers. Actually, these days, they don't even know if they're using prime numbers. They just have a strong likelihood that the number that they're working with is a prime, and they just go ahead and use it. It's possible to at least be fairly confident that you have a prime without actually knowing it. When the numbers are that big, you don't have fast ways of deciding whether you have prime numbers or not. Actually, that's the whole basis of the RSA crypto systems, the public key crypto systems that are in use today. Every time you put your credit card information into the internet, there is the RSA cryptography behind the scenes that's protecting your data. So it's very much based on the difficulty of factoring primes and knowing whether a number is a prime or not. So this is really just a baby statement here about relatively smaller numbers. For larger numbers, it's much, much more challenging. Actually, does anybody know how many prime numbers there are?
Yeah.
How many? There's infinitely many of them. Yeah. Do you know how to prove it? You do. Like, I should just like sit down and let someone else take over. Here's our good friend Euclid again. There are infinitely many primes. Yeah, let's write that one down. There are infinitely many primes. And this is something everybody in a class like this, I want you to know how to do this. And so we're going to write down the proof, even if you may have seen it before. This is proven, of course, by contradiction. So we will take that strategy this time. So let's just suppose that there's only finitely many primes. Suppose we have finitely many primes, and I'm even going to make them into a set here. Let's just list them out. If there's finitely many of them, we can like enumerate the full set of primes right there. Let's say P1 and then P2 and then up to Pn. Finitely many primes. And I might as well again assume that they are in increasing order, but this time strictly increasing order from P1 up to Pn, like so. And I'm going to construct a new number now from here. And let me call this new number capital P. And this is, by the way, this is really clever, the way that this contradiction is obtained. The tricky part of the proof is this next thing I'm going to do, which is construct a new number out of these primes. Okay, and it will be a number that is clearly larger than all of these numbers. So what I'm about to write down cannot be a prime number, right? Because this is all of the primes that we have. So what I'm going to do is multiply them all together, right? And then I'm going to just add 1 to that. Oh, this is so clever. Just going to add 1 to that. And this is a positive integer that is larger than all of these, but we just proved the fundamental theorem of arithmetic that this has to be expressible as a product of primes. Okay, so which is expressible as a product of primes. Which means that it must be divisible by one of the primes. Right? Okay, so P is divisible by some piece of I from my list. I is somewhere between, let's just say for some I going from 1 to n. It's got to be divisible by some piece of I. So in other words, piece of I divides my number here, capital P. However, we also know that piece of I divides just the product of the primes themselves without the +1 on it. Because this is multiplying all of the primes. So one of the primes that's in this product here is the piece of I itself. So piece of I divides this number and this number, which is just one more than the first one. Right? In other words, these two things are one value from each other, and piece of I is dividing both of them. So of course it divides the difference of them. Okay, so by subtraction, we're almost done, guys. By subtraction, this piece of I divides capital P minus the product P1, P2, up to Pn. And that means that is piece of I divides 1. Which is impossible, right? Because piece of I is more than 1. It's a prime, right? So this is a contradiction. So that's actually a contradiction. Sweet. So there's infinitely many primes out there. One of them is the even number 2. All of the others are odd. And if they're odd, then they would either be of the form 4k plus 1 or 4k plus 3. Well, so you might be wondering, well, are those also infinite? So could there only be, just like there's only one even one, there's a finite number of even primes and then an infinite number of odd ones. So when you go now and just looking at the odd ones, you could ask yourself, well, are there a finite number of like either the 4k plus 1 or the 4k plus 3 and the infinite ones are in the other pile, or are each of those sub collections also infinite? Turns out those sub collections are also infinite. So I could give you, another similar result that's just more precise than this theorem. And you could also pretty much just attribute this to Euclid. I'll just call this one, well, in the book it's theorem 3.6, and we'll just give Euclid credit for this statement as well. And this is, there are infinitely many primes of the form. So there's obviously infinitely many odd primes right now, but there are actually infinitely many odd primes of the form 4n plus 3. So if I just limit myself to numbers that are, well, to use modular arithmetic, congruent to 3 mod 4. These are all odd numbers, but they're specifically congruent to 3 mod 4. There's infinitely many primes in that form. There's also, as it turns out, infinitely many in the form of 4n plus 1, although that's actually harder to prove. So for the time being, I'm going to focus on this easier statement, because this one is proved by just tweaking this proof slightly. Otherwise, it's basically the same proof. I guess I'll try to prove it as well. And then I was gonna do some group work today. We'll see if I get to it. Otherwise, I'll just have to wait till Tuesday. But I'm gonna let you practice one of these as well. There's also infinitely many primes of the form 6n+5. For example, so that you can change this up and you just have to take, it's the same basic argument, you just have to tweak it a little bit. Yeah. So here's how you would write this one down. You guys probably will see this coming just as fast as I'm writing it down. This is also done by a contradiction argument. And so we again start off exactly the same way. Suppose we have finitely many primes of this form, right? And then we go from there. So suppose the set of primes of the form 4n+3 is finite. So just to use different notation for this proof, I'll use Q's again on this proof, so it doesn't get mixed up with the previous proof. Let's say Q1, comma, Q2, comma, dot, 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 up to Q sub S. Let's use an S for this one. So suppose you have finitely many primes of that form. And now I'm going to again create a new number. And this new number that I'm going to create is going to be, I'll call it capital Q. Again, just kind of mirroring the way I did the argument just a moment ago. But this Q is going to be written in it. It's not just going to be the product of all the Q's plus one. I need it to still have the 4n+3 form. So the way I ensure that is I'm going to do this. This is such a trick. I put my factor of 4 down there, and then I create parentheses around the product of all of the Q's. I'm going to subtract 1 from that. Okay. And then add 3 outside. Okay. Now add 3 on the outside of that. So clever. So clever. So this is this is going to play the same kind of role that the P did over there. Again, this is expressible as a product of primes. Okay, so which is expressible as a product of primes. So it'd be really kind of nice over the weekend for you to sit down with these proofs, see if you can kind of understand, well, why did they choose that? Why did they choose this? Because that's actually the key point in the proof. So you really want to try to give yourself some quiet time to sort of sit down and think about it. Like, why does this make the proof work? Okay, so let's see if we can figure it out together. So we've got this thing expressible as a product of primes. So I'm going to write Q as, let's say, R1 times R2 times dot, dot, dot times RT, where all of the R sub i's are primes. Actually, I can be more precise. These are all odd primes. Does everybody agree with that? If one of these R's was even, then Q would have been even. But I can look at Q and I can see that Q is not even. So the R's actually have to be odd primes. This is since Q is odd. Right, so these are a bunch of odd primes being multiplied together. So each of these R sub k's is odd and prime. So if it's an odd number, then it has the form either 4n+1 or 4n+3. We don't know which one, but it's an odd number. R sub k is odd. So each R sub k has the form of 4n+1 or 4n+3. Every odd number is going to have either this form or this form. Now, if every one of these R's was of this form, if, I'll say it first and then I'll write it down. If every one of these R's was of this form, so you had a 4n1 plus 1 and a 4n2 plus 1 and a 4, if they were all of this form and you FOILed this out, you'd get 4 times some big thing with a big plus 1 hanging on the end of it. Well, that's not how Q looks. Q does not have a plus 1 hanging on the end of it. It's 4 times something plus 3. Right? So if every one of my R sub k's had the 4n plus 1 form, the result would be that Q also has that form, which it doesn't. And so I'm going to conclude in a minute that at least one of these R sub k's must be in the 4n plus 3 camp, which means it must be one of these Q's. Yeah, that's going to be the argument. So I'll write it down. All right. So did everybody follow that? Okay, it's the same proof that we gave over there, but just with a slight little extra step here that we have to talk about. Okay, so the point being that I'll just make this maybe as a note. Since the product of integers of the form, okay, so since the product of integers of the form 4n plus 1 results in another number of the same form, since the product of integers of the form 4n plus 1 results in another number of the same form, and we're multiplying these r's together to get q, right? We conclude, since q doesn't have this form, we conclude that since Q does not have this form, that there exists, let's see, what did I call it in my notes here? There exists an I such that R sub I is equal to the form 4n plus 3 or some n. Yeah. I'll slow down a little bit. It's a fair bit of writing on that. But that just means that R sub I is actually, I mean, we know it's a prime. We know it has this form, and we listed all of those here. So it has to be one of those Q's, right? So R sub I is equal to, I chose Q sub j or some j. And so thus Q sub j, if it equals R sub I, it has to divide the capital Q. Right? So if the Qj is one of my R's, any of my R's divides Q. But actually, Q sub j also divides just the product of all these Q's as well, right? So also Q sub j divides, I'm actually going to put the 4 with it as well, 4 times the product of all of the Q's. Q1, Q2, Q3, all the way up to Qs. So let's just get this clear. Q sub j divides this whole thing, but it also divides just this much of it. And if you think about it, other than just that much of it, you have a -4 and a +3 after that. If you were to multiply it out, yeah? So just like before, I'm going to make the difference of these two numbers, and Q sub j will divide that as well, right? So Q sub j will divide capital Q minus 4Q1 times Q2 up to QS. It will divide all of that. And if we take this whole entire Q and we subtract just the underlying part, we're left with -1, I think. Or Q sub j divides -1, and this is a contradiction. Yeah. So that's a contradiction. So it's the same kind of contradiction. The argument is basically the same as the original proof, but it has to be kind of, spiffed up just a little bit to make it work. Spiffed up just a little bit. Questions here, guys? Does this make sense? So it's something worth spending some time thinking about. Yeah, Brian?
So in the first example, we wanted Q to be a bigger number than the product of primes.
Yeah, we took all the primes together and we just added one.
But
Yeah.
in the example we just did, Q is less than.
It is actually, I mean, you would, you might say, well, what if I put a plus here or something? And you could ask yourself, would that still work? And actually, this is kind of what I was talking about over the weekend to figure out, well, why is this what it has to be? If you put this into a plus, then actually what you have is like, +7 on the end of this expression rather than a +1. And so if I subtracted them, I'd get something like Q sub j divides 7 instead of -1. And now if Q sub j divides 7, I have to say, oh, well, then Q sub j could equal 7. And that wouldn't be a contradiction, right? So somehow you have to have the +3 here on the end of this one to make sure that Q is not just a product only of the 4n+1 numbers, that there has to exist one of these at least. So that's why you gotta end with a +3. But if you put a +1 here, like we did over there, then it doesn't quite work. Yeah, so it's good. I'm glad you're asking that question. I mean, it's the kind of question I want people asking. Think about, well, why does this proof have to go kind of exactly the way I framed it here? Yeah, go ahead, Tony.
Why does the R sub I have to be odd?
Why does the R sub I have to be odd? If any of these were even, if any of these was an even number, the product would be an even value for Q. And I can look at this and I can say, I can already tell you that Q is not even. Ooh, because this has got a multiple of 4 with 3 added to it. So it's actually become an odd number.
Okay.
Yeah.
Thank
That
you.
make a little bit of sense? Okay. On next Tuesday in class, we're gonna do some group work together, and I'm gonna have you try and prove that there are infinitely many primes of the form 6n plus 5. So one thing I might recommend, actually I should have said this even at the start of the class, because we only have class on Tuesdays and Thursdays, it's very easy to sort of drift off, at least with the lectures for 4 days with not hearing anything from me. And then so if you come in here on Tuesday and you haven't thought about anything since the previous Thursday, it might be a little hard to jump in. So just in general, a good piece of advice, just study wise, if I was a student, I'd probably do this, would be to just review your notes briefly on either Monday night or Tuesday before class, something like that. So that this would be one thing I'd want you to review, because we're going to have you guys try to mimic this proof for the 6n plus 5 case. Okay, so how do I need to tweak it to make it work, and then run through the argument. So that'll be great. We'll get a chance on Tuesday to reinforce this idea of how the proof works, and kind of go from there. I was going to do it today, but I don't think I quite have enough time, and I don't want to rush the group work. So we know that there are infinitely many primes, and even infinitely many primes of certain forms. It leads to another question. If we've got an infinite palette of prime numbers, it's sort of an interesting question of like, how are they distributed? And what do they kind of look like? Are there any patterns at all with how these primes go? And so that's a natural question. I want to say a little bit about that. So a question here, I'll pose this one, that we could try to answer is, how are the primes distributed? Right, and I made some kind of joke the other day about how the fact that later this semester, I will be back in the prime of life again. My age will be a prime number, but that it hasn't been a prime number since 6 years ago. And after this year, I'll have to live it up fast because I'll be out of the prime of life again for several more years to come. You guys are probably in and out of the prime of life much more often. So the primes seem to get scarcer. That would be something I think we would all probably intuitively agree to. The primes get scarcer as you run down the number line to larger and larger numbers. However, there is an interesting thing called the twin primes, which is the concept of a twin prime is just two prime numbers that are just two apart from each other. So just as an interesting, I'll make this as a definition. P and Q are twin primes if they are prime and the absolute value of if I subtract them, the difference is only 2. So when you're in this scenario, you can be in the prime of life 2 out of 3 years, right? You go in, then you go out, and you go back in again. So just as a couple of quick examples, I guess the smallest one would be 3 and 5. They have to both be odd, obviously. 3 and 5 would be twin primes. You could do 11 and 13. Those are both primes that are just 2 apart. But you can find some bigger ones, 71 and 73, and so on, like that. And this leads us to the first. I told you, I think, that number theory has some incredible conjectures that are out there that are easy to state, but which are very hard to prove because they haven't been proven yet. And the twin prime conjectures is one of them. I'm going to write it down here. If anybody can prove the twin prime conjecture, you'll get an automatic A+. You won't have to come to any more of my classes. Just be sure to put my name on your paper when you're famous. I took this class from Dr. Annan. He told me about the twin primes conjecture. So yeah, the twin primes conjecture is the following. This is kind of just a bit of history, which is just that there are infinitely many twin primes. I'll just say twin prime pairs. There's infinitely many pairs that consist of twin primes. Such an easy statement, 7 words long, and it's been around, of course, forever, and it is still to this day an open conjecture. The twin primes conjecture really says that there are infinitely many pairs of primes that are 2 apart from each other. Now, in 2013, which actually is not that long ago, in 2013, it was finally proven that there are infinitely many pairs of primes that are within 70 million of each other. Right? So that was the best I could do. And that was just 12 years ago. It has since been improved. Now the current knowledge about this conjecture, it hasn't been proven. The current knowledge is that there are infinitely many pairs of primes that are within 246 of each other. So there are infinitely many pairs of primes within 246 of each other. Actually, it's kind of funny. People will often ask me, oh, so you're teaching this theoretical class on number theory. You must just go back to your notes and just recycle. the same notes every time you teach it, because nothing changes, right? I'm like, actually, some of these conjectures are being worked on, and I have to like update my values every time I teach it, because the results are getting sharper as we go. But 246 is still a long, long way from 2, right? If this said there are infinitely many pairs of primes that are within 2 of each other, well, that's the conjecture, as stated. Yeah, Bobby?
If this conjecture is true, what consequences?
Ooh, that's a good question. So it turns out that this conjecture is related, very related to something that's probably even more famous than this, called the Riemann hypothesis. For the longest time, that was sort of considered probably right behind Fermat's last theorem as one of the most famous unsolved problems in the world. And the Riemann hypothesis is not a twin of this result. It's more like a cousin of the result. It's very similar to the Riemann hypothesis. If we prove the Riemann hypothesis, which has to do more with just the general distribution of primes overall, if that turns out to be true, it still won't even prove this result. But it's very, very highly related to it. So it's one of those things. I mean, did your life change very much when you found out that Fermat's last theorem was proven? It's kind of, I hate to say that in number theory, we often are inspired by the curiosity, the challenge of it. It's something so simple to state and think about, but will it have grand applications? I think only time would tell. I'm not sure. It's one of those things that people are interested in it for its own sake. And why not? I mean, it's such an easy thing to write down. Yeah, so it's generated. It also has the potential and has generated a lot of other math. Just the process of working on the conjecture. So sometimes you get unexpected results that aren't even in the direction that you're working on with the actual conjecture itself, and that can be also quite interesting to think about. Sorry, just checking. Oh, I'm basically just about out of time. Oh, it's also possible to make, so there might be infinitely many times when there's 2 primes that are 2 apart, right? But I can promise you, this is not a conjecture, this is true, that if you give me any number whatsoever, could be 5 billion, I can find 5 billion consecutive non-primes. I can make such a long scarcity of primes as long as you want me to. Okay. So and actually, I think on Tuesday I'll start off. I'll just write down how you do that. It's actually not that hard to make a string of composite numbers that is as long as you want. We can do that. So that means that at least on some parts of the number line, there's no primes anywhere in sight, right? But then somehow we can't seem to disprove that somewhere later on that number line, there's going to be 2 out of 3 numbers that are prime. Isn't that crazy? It's actually quite interesting to think about. But I'll have to save more of I get excited. I have to save more of this story for next week. We'll talk a little bit more about primes. I also will start talking about modular arithmetic. Somebody asked me whether you can use it on the current homework. Totally okay with that. But we'll get into it formally next week as well. So guys, I'll be heading downstairs. If anybody wants to stop by, if you got questions, want to talk about number theory a little bit more, I'll be there. Have a great weekend. Shoot me an email also if you have questions. You can do it that way. And we'll be in touch. Bye for now. Thanks. Appreciate you being here, guys.